The area bound between two intersecting curves. The two important things that we need to remember is to first find the points of intersection, and of course there are a few different methods in which we could do so. One is doing it on the graphing screen, the other is using the calculator screen. So we'll explore both the methods. Now these are some of the exam style questions, and the first example that I've got over there is find the area bound by the curve. So the first function is x cubed and the other is negative x whole cube plus 4x, and both of them lie in a domain of negative 2 to 2. Now we have just drawn a graph. However, I'm actually going to show you how we are going to do this graph. So if I go to menu and insert a graphs page, and we are going to do our first function x cubed. I'm actually going to ignore the domain on this particular page. So that's my first graph, and then if I do control G, let's do the second graph, which is negative x whole cubed and plus 4x. So I do get a graph. Now I don't really need that much on the scale, so if I change that to maybe negative 3 and tap to the next point, probably change that to 10 and tap to the next point 3 and then tab there and maybe go to negative 10. So I get a graph where I can clearly see the points of intersection and everything. I'm just going to move these out of the way. Now I'm going to use the graphing method first. So if I go menu and analyze graph, and then number 8 is bounded area. Now if I put my cursor there, and that seems like 2, and if I start moving it there, I can actually see it starts shading the area, and I keep going until I get to this point there. I think I put it at 2 by default because I've got that area as 8 and I know that the area is 2, but let's go and check that there is, yes, negative 2, and that there, if I put the coordinates, that's 2. So clearly from negative 2 to 2, these two curves have actually enclosed an area of 8 units. So that's actually doing it on the graphing screen. Go to menu, and I've got a system of equations. I can determine the points of intersection. So if I go algebra, that's 3, and number 7 is system of equations, and then I'll use number 1, and it says I have 2 equations. So let's go and use the template. So that one there is clearly y equals x cubed. I could have used f1 there, but I'm actually just going to enter it in terms of y equals negative x whole cubed plus 4x, and now if I solve, it gives me the points of intersection. So I've actually got a whole lot of these points of intersection. So that's the way I had entered that, and you can see all the solutions. I've just put it on the screen so you actually see all the solutions. So these are my bounds that I'm going to work with from negative 2 to 2. So now we are actually going to use the anti-differentiation template, which is menu 4 and 3. So once again, if I go to calculator pay template, sorry, I should have been there, menu calculus and the anti-deriv template. So I put the lower bound there, the upper bound there, and the two functions. In my case, I've already actually got the functions defined. So if I do f1, it picks up the function, and minus f2. Yeah, so that's f2, and once again x and dx. Now my lower bound is negative 2, the upper bound is 2. Now actually I can do it in parts, but I'm going to do the quick way. I can select this whole bit here, and if I go actually here, I've got this template where I put the absolute value, and if I do that, that actually gives me the equation. So I didn't have to worry about these limits. However, I can actually find it in parts, and I'm going to demonstrate that on now you can see I'm doing that in parts. So that's one way of doing it. That's the second way of doing it. So in this case, the function that is on top comes first. So within that domain, from -2 to -√2, f2 is on top, and then in this domain f1 is in top, and you can see they are alternating. So that's one method. The other is to swap put negative in front of these, so that it will treat those as positive values, because you're finding the total area. And the third one is to just swap the limits. So over here and here I've swapped the limits, so all three are actually going to give me the same area. So that's what I have. That's really it. Now this is a question that you need to try. Determine the area enclosed by these two curves, and you will see if I go back, one of them actually is in polar form, and you need to convert that into Cartesian form. So when I convert it to Cartesian form, that's what it translates to. Now you will see it's a very simple quadratic. So these are the two. So one is a square root function, the other is a quadratic, and I've just used the graphing screen. I've plotted both, and I've done menu 6 and 8, and it gives us the area. And if I use the absolute notation that I've done, I get that area as 10.66 approximately, and that's in the exact form. So these are a few questions I would like you to try, and you will also find these questions in the TI Inspire TNS file that will accompany this video presentation.